Hello, my name is Christian Favis, and this is my project 2 for Dr. Ozbay's aerodynamics class. Today we're going to be doing representing combined Poisel and co-et flow in ANSYS Fluent. It will be a 2D. It's parallel plates, and we will be having the top plate moving at a velocity of 3 meters per second to the right, and the bottom plate moving at 2 meters per second to the left. Length and height should be chosen, but make sure length is 150 times the height. But make sure that with those lengths and heights that you choose, that the Reynolds number stays under 2500. We can use any fluid, and I will show that we will be using air. So start off, open up Workbench, find on the left side fluent, drag it out onto your schematic. Drag out the schematic. Click on geometry once. Go over here, change it to 2D analysis. Click geometry, new design modular geometry. And then just wait until that loads completely. It may take a little bit. Just give it some time. All right, now we're in the design modeler. Change it so we're looking in the XY plane. Go to sketching. Let's real quick change units to millimeters. We're just gonna create a simple rectangle centered at the origin. Okay. Again, my computer doesn't really like ANSYS Fluent, so I apologize for the visual errors that you will see, but everything still works the same. Draw the rectangle, go to dimensions, horizontal, click the bottom 2 points, the bottom 2 corners, drag that out. There's your horizontal length, and then the vertical length. Click these two, then drag it out. Boom, vertical and horizontal length. For the horizontal length, we are doing a length of 450 millimeters. Makes the thing quite large right here. 450. And for the height, we are only going to do a height of 3 millimeters. You should see that right here. Again, 3 times 150 is 450. So our conditions are satisfied, and it's quite small, but we will be satisfying the less than 2500 Reynolds number for the flow of this. So next, go to concept, surface from sketches, click the thing, one of your edges, click apply, should highlight the whole thing, then click generate, and just like that, you should be able to see the whole entire should become shaded in. So I believe that's it for that. Now we gotta start our meshing. So when you come back out here, you should see a green check mark for geometry. So click the mesh, double click mesh actually, and then wait a second for that to load. Okay. All right. So we're here. You should see your rectangular mesh or your rectangular geometry earlier. Real quick before we do anything, let's create some name sections. You do that here. Make sure you click the edge tool up here with the green edge highlighted. Click your top edge, or you can click wherever. Click N once it's highlighted. Let's rename this to top wall. Click OK. Click bottom edge. Rename by clicking N. Just see bottom wall. Click OK. Let's get this outlet. Click OK. Click this one. Inlet. All right. Click OK. Let's zoom out real quick. Change the thing. All right. You should see top wall, bottom wall, outlet, inlet. Okay, that looks good. Yep. All right. Now we want to actually begin designing our mesh. Right click mesh, click insert, face meshing, just click the mesh, apply. All right, good. Now that's added. Then we want to add some sizing. Zoom in, hold control. Oops, do not click that. Make sure you have edge selected. Right click the top or left click the top while holding control. Left click the bottom as well. Click apply. Should be two edges. So it should show up like that. We are going to do number of divisions, and we want to create a mesh that is accurately captures the flow. So for this, I believe I'm going to do 800. Yes, 800 divisions. We don't want any curvature, and we want the behavior to be hard. So we want ANSYS to for sure follow that. We want 800 divisions along the top and bottom. And now we also have to do the inlet and the outlet. So go click inlet, left click the inlet while holding control, go to the outlet, boom. All right, apply. You should see that it says two edges. Then we're gonna do once again number of divisions. This is how many divisions we want along the pipe, or not pipe, but the rectangle that we're gonna be meshing. And I believe I use 80 as the number of divisions. Yeah. Turn off the curvature, and then set the behavior to hard. After that, your mesh should be good. So click generate, and then it should take a second for it to load. It should become dark, like this, but make sure you have mesh highlighted and zoom in, and you should see many little rectangles, straight rectangles. And this will be good for our analysis of the flow. So that looks good. Meshing is done. Make sure you have all your name sections or selections. Come back over here, update your mesh, and wait for that to update. Nice. Now we can go to the setup part. Setup, we are going to do double precision and two solver processes. Again, the solver processes is based on your machine, how strong it is. And just again, wait for that to load up. Should take no time at all. So this is where we are going to go show our velocity contours with vectors. We're gonna zoom in. We need the pressure contours, velocity profiles at the mid and end section, maximum velocity and the height, and determine pressure gradient. Okay, so let's go back. Here's your thing. It should show the inlet, the outlet. Nice. First things first, go to setup. All right, we're doing a laminar project. Click OK. Change it to laminar. That's good. Materials. Today this time we're going to be using air as our material. So these are the values, and I already used these numbers to calculate that the Reynolds number will be less than 2500 with our given design. You are free to change the density as you wish and the viscosity to help you manipulate that Reynolds number so it actually becomes less than 2500 to represent a non-turbulent flow. All right, next, go to boundary conditions. We are going to go to inlet, double click inlet. And then so our velocity inlet 5 meters per second. Apply, close. Remember, pulling back this up. This is a free stream incoming velocity of 5 meters per second. The top velocity will be going 3, and the bottom velocity is at -2. So, oops. Apologies. Going back to the flow. We set the inlet to be 5 meters per second. Good. Top wall, we're change that. Double click the top wall. Make sure it's a moving wall. Make sure the motion's absolute. And the speed will be 3 meters per second. Apply, close. All right, now we do the bottom wall. Moving wall, absolute, speed 2 meters per second, but in the direction of -x. Now, yeah, should be good. Top wall, bottom wall. Okay, what I like to do again is make sure that my solution pretty much converges. So I like to add a couple of zeros. Well, when we're solving it, just click OK. Then we initialize and then we run the calculation. Make sure your iterations that you run can be at any amount, but we're doing 200 for this one. As you can see, our process is finished, and now we can begin analyzing. First things first, let's go back to the assignment. You want a velocity contours with vectors. All right, so there's two ways to do this. You can do this on this page, but you could also go into the results section, which is in over here. Do that. I'll show you this way. So what you want to do, go to graphics, contours. Rename this to something you know or you want it to be known as. So we're gonna just rename it to velocity contour. Velocity magnitude, and just highlight the whole thing. Save and display. All right, now you can see the velocity magnitude. You can see how it goes from the top to the bottom, from where it's highest over here, but it still has that 5 meters per second to the right. And if you want it to be more like accurate, you can just change it to x velocity, where your minimum will be -2, and it will show that it will be the same thing. 7.48 or whatever, however high it reaches, and then it's still like around 5 up here, and then it's -2 as by the what it says right there. But make sure you make that velocity contour, and then we still need the vectors. So go to vectors, right? And then we could just name this velocity vectors. And we're just going to have velocity vectors, color by velocity, and then we're going to do x velocity. And just highlight all of those, save and display. It may take a second. If you're too far out, it's not going to show. Make sure you're zooming in. But here they are. You can kind of see them. It's a little bit difficult to see at times. So what you can do is change the scale. Like, let's say half the scale. Save and display. And now they're not also jumbled up. You can see my velocity vectors as they go. This represents the moving wall or the moving plate at the top, going at some speed, and it goes increasing. But then at some point between the bottom, it actually reverses so that the bottom plate is actually going -2 meters per second to the left. So if you want these on top of each other, you can go to scene. We can just name this velocity vector / contour. You can name it whatever you want. Make sure you have both of those on. You could do this. Watch. You click both of those, do save and display. Sometimes it gets hard to see, so you might want to change the transparency of like the contours. I like doing 40 roughly. And yeah, so here's your velocity contours with your vectors. Far away, obviously, it's not going to look like anything because your aspect ratio. Here's what it's looking like in the developing region. And somewhere around the middle, it's like fully developed, and you get something that kind of looks like this, where you goes increases, and then it reverses somewhere along the way to the bottom. So that's how you get that. Let's see what's next. Pressure contours. Pressure contours. Again, go to contours. You could just rename these like your pressure contours, so you don't mess with the velocity ones, and you just highlight everything again. Pressure, static pressure, save and display. You can see that the static pressure slowly decreases as we go along the two pipes, or not two pipes, excuse me, the two parallel plates. There's your static pressure. Take a picture of that. Zoom in if you need to. Here's the dynamic pressure. Take a picture of that. You're free to zoom in as well to take a closer look. This is what it looks like as the flow speeds up. The dynamic pressure is also increasing. And here we have the total pressure as well. Total pressure kind of looks something like this in the middle, and we can see that the total pressure overall decreases as well, but it's mostly high in the beginning. So there's that. There's your total pressures and stuff. What else we have is to show the velocity profiles at the mid and end section of the pipe. Okay, so what we want to do is make an XY plot. Yes. We can do, say, title this like velocity profiles or whatever you want to title it. The plot direction will be in the Y direction. Note that. Make sure that you position on the Y-axis, and we want the X-axis to be the velocity, and we want it to be the X velocity. And it said the midline, so, and the end line. So remember, we want to make this a new line for it to take to measure at. So our midline is going to be at x equals 0. I believe 225. 0.225, our x0. Yes, because our total length is 0.45. Right. And then so it's gonna, since we have our bottom at the center line, our y0 is gonna be 0, and our y01 is going to just be the overall height of our pipe in meters, which should be 3 millimeters. So click create, and then we just need to change this to end line. And you would put the end line, just change these x values to like 0.45 for 450 millimeters, but I like to change it to 449 just right before the end line, because sometimes it does not like to accurately grab the end. So I like to do that. Do create, close, and then just click your end line and midline and save plots. And you should get to see these your plot, your end line and your midline at the same plot. Again, like the project before, you can write to file, get it to Excel. You can analyze the data, the values, and that will be all nice and dandy. You see that it actually has a velocity of 3 at the top, which is expected. And it increases, but as it gets towards the bottom, because the flow is actually going to the left, it goes all the way to -2 as the x velocity in the to the left. Um, so that is the velocity profiles in the mid and end section. Determine the maximum velocity and the height at which the maximum velocity occurs using fluid results. Okay, using the fluid results, we are going to do a surface integral, and we will be doing a vertex maximum of the velocity magnitude of the whole surface, and just compute that. It will show you the maximum of like the maximum velocity. We get a 7.478437. Um, and that is roughly what we get. Yes, if you go all the way over here to the end, 7.47. I believe I saw just 7.48. So if you round up over there, I'm sure you can get more accurate answers if you take the velocity profile, but you can see that it will be over there. That's the max. Let me write to file. Right. Uh, and you can see the height. You can use your Excel files as well to load it up, which I will be doing right now. You pull up Excel. Actually, the way I find this easiest to is actually is to open the download file into to to Notepad and just export it to Excel. So there's that one, and then here we want our midline. Which we get that. And then you can just like look at it, and then you can filter it, sort from largest to smallest, sort. See that you can see that the maximum velocity is at 7.4179, but it occurs at a height of 1.7 millimeters. But in this one, if we do this, oops, my bad. (7.46458) at around 1.763 millimeters from that graph as well. So once again, that's how you get the close to the max values. Moving on. Finally, you want to okay. Finally, you want to determine the pressure gradient using the fluid results. You can then move on to we are going to do one more surface integral. And we're just going to find the midline and endline, and we are going to do an area weighted average, get the pressure, static pressure, and then compute it. Now what you want to do is that you get the end line and subtract it by the midline, so you get the total pressure, static pressure. So I believe negative 0.072841053 subtracted by 23.607397. You get negative 23.68023, and then you want to divide it by the length that we're measuring, which is half of the total parallel plates. So we divide it by half, and that will be 0.225. And so with our value that we get is around negative 105.24 is our pressure difference. Um, we can see that in here that I did some math and I calculated that the pressure difference will be around negative 107.364. So we are quite close to the expected value. So the theory and the measured results are very close. As you can see, this is the Reynolds number that I calculated. It is well under 2,500. And these are the error and the values that we will be using to measure this flow. So I believe that is about the end of this project. I showed the velocity contours, pressure contours, velocity profiles, maximum velocity and the height. And I determined the pressure gradient, showed the theory, handwritten. And so yes, that's about it. Um, I also calculated the max height that it would occur in the theory, and it's very accurate. So thank you guys, thank you for watching. And this was my project too. Bye bye.